My thesis is about complete flow description from combination of incomplete measurements. And as we know, the pressure field is very important in aerodynamics and turbulent research and aeroacoustics. And traditionally, the measurement is point-wise or use pressure-sensitive material, which is usually point-wise or on the surface of objects. On the other hand, we can compute the pressure field from the time-resolved Navier-Stokes equation, which requires the temporal and the spatial information of the velocity field. And as we know, PIV can measure the velocity field, and there are in general two sets of PIV. One is for low speed flows, and which can measure the time resolved velocity field up to zero point 0.1 meter per second in a huge amplification rate. And for the high-speed PIV system, the speed it can be up to 10 meters per second. So there are still limitations on the temporal resolution. On the other hand, the probe can reach very high sample rate, repetition rate, even up to 10 million hertz, but they are point-wise. So my objective is to obtain the time resolved velocity field from the combination of PIV snapshot and high repetition rate sensor signal, and then integrate the pressure field. Here is a sketch of how my thesis is working. Firstly, we are we are building the correlation between the PIV snapshot and the probe data. After that, the time resolved PIV can be reconstructed using the probe signal, and the pressure field can be computed from the via the Navier-Stokes equation. And the first work of this year is the offline sensor positioning. As we know, a better sensor positioning can both improve the accuracy of velocity field and reduce the number of sensors. And there are two ideas to place the sensors. The first one is online optimization. And the experimenter will try every possible position of the sensors and select the best one. And the second idea is offline optimization, which is doing one preliminary velocity field measurement and compute and test the best sensor position from the PIV data. And my work has some results. First one, the offline optimization is sufficient for sensor positioning. And second, the accuracy is improved when we considering the correlation between upstream and downstream. And the third one is a planar preliminary experiment is often sufficient for the later experiment in three-dimensional. And here is a paper published, and the code and the data is open sourced online. The second work is machine learning with overabundant unlabeled samples. And here is the idea measurement of the velocity field, which is time resolved. But actually, due to the limitation of experimental facilities, we can have only very few PIV snapshots due to the limitation on the temporal resolution. On the other hand, the probe signal can be very high, repetition rate. But unfortunately, we can only use very few part of the probe signal and discard most of them in the supervised machine learning. So the strategy consists of two sides. The first one is to generate more velocity field using physics models, and the second one is to use semi-supervised machine learning that utilize the probe signal not labeled by the velocity field. And the whole process is a bit complex, and one good idea is to introduce another model that not to estimate the temporal mode of PhD coefficients, but to estimate the temporal derivative of the periodic coefficients. And in the Model G, the training doesn't require the label from the PIV snapshot, so that the utilization of probe data has significantly increased. And the last column is the result utilizing the overabundant machine learning overabundant unlabeled probe data. And you can see the improvement. And we are writing the journal article of this work. And the side work is on the filter of PIV data. For example, here is a time series of PIV measurement. And we are going to propagate the velocity field from the series of measurement in a close time to the same time instant using a physical model. Partial U over partial t is a function of the velocity field at any snapshot. And here we are using the advection model, which is validated in a short time period. And after that, we have several PIV snapshots on actually the same time instant. And we do the filter on the corresponding position, which is actually the filter along the trajectory of the flow motion. And thus we reduce the size of the filter size and pertain more flow details. And this filter is done iteratively to improve the result, and we call this method advection-based multi-frame iterative correction, or in brief, AMIC. And here is a result of AMIC. The last column is the pressure field, and the first column is the clean velocity field, and the velocity field superimposed with Gaussian white noise and the noise with spatial convolution, spatial coherence, because the overlapping of interrogation window is widely applied in PIV to enhance the vector spacing, so that the error has somehow spatial coherence. And the field, the velocity, the pressure field directly computed from the noisy field in some degree. And the surface Gola filter, which is spatial temporal filter, which can work well when the velocity field with Gaussian white noise, but field with when the noise with spatial coherence. And POD traction field and AMIC can work for both cases. And this this method is also worked for experimental data set, and we publish paper, and the code and data is open sourced. And the final part is a research day. I have research day on the Shanghai Jiao Tong University about the physics informed neural networks and transfer learning between the simulation and the real flow. And here are some outcome of this year. And thank you for your attention.